Good day, stat students. So today we're going to talk about section 10.4. Here the samples are dependent, and we're going to be running a paired t-test. Some books might call it a matched pairs test, and that's fine. But we're going to call it a paired t-test because that's what this textbook uses here to refer to this test. And so, remember, Chapter 10 is all about the comparison of two population means, and that is still happening here. However, the samples are dependent. And so what's going on here is the following, is that you have population number 1, you have population number 2, and remember what we said before, is that what's going on here is that maybe you have this before and after situation, and so you have person in population number 1 and before. Now, like the example that I'm going to give here in a little bit, the people went ahead and took this new pill to see if it was effective in lowering cholesterol. Okay, and so you have the cholesterol before, and then they took the pill, and then you have their cholesterol after. And so it's exactly the same people. Okay, and you want to compare. So what is this person's results going to be compared to? Well, basically themselves, right? It's just before, after, before, and then after. Okay, and so you have this natural pairing going on, and this result can only be compared to this result over here. And so you have this natural pairing going on. Okay, and that's what's going on in section 10.4. Okay, to me the best way to do this is just start working on a problem, and you'll see why. So example number 1, a pharmaceutical company created a new medication to help lower total cholesterol. The company measures 15 people's cholesterol before and after they are given this new experimental medication. Because why? They got to get FDA approval. So the following are the data for the 15 random individuals. Now before we do that, let's define a few things. We're going to go ahead and say individual. So individuals before the medication is population number 1. Individuals after the medication is population number 2. Okay. Here's the data. So here's population number 1. Here's population number 2. Before, after. Okay. And so notice I've created here another column. I call them the difference column, the D's. Okay. This is actually probably the most important thing in the whole thing, in the whole analysis, is the D's. Why? What happens here is that what we're going to do is we're going to simply do the subtraction between the two. Okay. So before minus after for each individual. Okay, and that's what the D's are standing for here. Okay, but I want to stress this, is that what we're doing is that we're creating a whole new random variable. We took two variables, before and after, and did the subtraction between the two. And when you do the subtraction between the two, basically you've created a whole new random variable. So you've taken a problem that had two variables and shoved it down to one by doing the subtraction between the two. That's kind of cool. Okay, and so all the analysis will be done on the D's. Okay, that's our new random variable. Okay, so normally our random variable is what? X, right? But here, because we did the subtraction between the two, it's the D's. Okay, so let's take a look at the first person now. If you didn't have your calculator, go get your calculator and come back. Okay, so let's assume that you got your calculator, and let's take a look at the first person. So we have 243, and you would do the subtraction. Now you're going to have to do this for problems in WebAssign. You're going to have to do the problem like this on the exam. So let's just go ahead and get used to doing this. And so you have 243 minus 201. You got a difference of 42, and you got to pay attention if these differences are positive or negative, positive or negative. And so notice for the second person, we got 234. We're going to do the subtraction between the two, 207. You get what? A difference of 27, positive 27. Take a look at the third person. Third person is 238 and 240. You do the subtraction between the two. What happens is that you actually get a negative 2, Okay? So you have to pay attention to the positives and negatives for the differences. Okay? That's really, really important. So I'm going to fill in the rest of these. Okay? Hopefully you're good with all those numbers. All right, there are all the differences. Okay. All right. Please pay attention to this next thing. It is vitally important to understanding the test. So there's a major step that I've never seen this in a textbook, and I've never seen even another professor even do this. But I guarantee you it will make your life so much easier if you do this step. Do not skip this step. Okay, even though the textbook doesn't tell you to do this, even another professor might tell you not to do this. I'm telling you that if you do this, it will help you define everything going forward for this test. Trust me on this. And notice what I did here. I said define what a negative d and a positive d means in terms of the problem. And what we're going to use is a bunch of common sense. Common sense prevails with a paired t-test. Okay? So this is what I mean. So let's start with the negative. So we had one person that had a negative d. Now let's think about this for a moment. Common sense. Cholesterol. Do we want high cholesterol or do we want low cholesterol? I think we want lower cholesterol. Okay? And so notice what happened for this person. Their before went from 238 and their after is 240. And so was the pill effective here? Was the pill effective in lowering cholesterol? Which way did the cholesterol go? It actually went up. And what did that do as far as the difference column? It actually created a negative. Okay? And so a negative D means that the pill was not effective. And so a lot of times with this before and after, we get to test whatever has intervened. So this new medication, this new pill, that's what intervened. Okay? And so we want to test that. Was the pill effective on average for the potentially for the entire population? Okay? And so a negative D means it wasn't effective. Okay, it didn't work. Oh, what about a positive D? Well, we had a positive D in all these people. Okay, I don't care which person you take a look at. Let's take a look at this person right here. 237, 230. We did the subtraction between the two. Okay, we got a positive D, positive 7. All right, and what happened there? The cholesterol went from 237 down to 230. So, was it effective in lowering cholesterol during this time frame? Yes. And what happened here is that a positive D showed up. And a positive D showed up here, here, and actually all these people right here. Okay? And so a positive D means that the pill did work. Negative D in this situation, now I'm not saying, now I want to be clear on this. It doesn't mean that a negative D is always bad and a positive D is always good. You have to look at the problem and use some common sense. Okay? Can you do that? Can you use some common sense here? I hope you can. Okay? Because common sense will rule and help you determine things statistically going forward. And so in this situation, a positive D is a good thing and a negative D is a bad thing. Okay, let's move forward. So this is what the way we think of it then in statistics. If the mean difference, so if the average difference, okay, the mean difference, the average difference for the entire population, now this is just for 15 people, but if the average difference, if the mean difference for the entire population is a positive number, then why? Remember what a positive meant? Positive meant that it's working. So on average, if the differences were positive, that means the pill is effective on average in lowering cholesterol. Okay? So on average, if we could show for the entire population, okay, that the differences are positive, that means that's a good thing. That means the pill is effective on average in lowering cholesterol. A positive D greater than 0. Greater than 0. Think about that. We have a name for that. So notice here we have a mean of a population, and so we call it mu, okay? But it's not for the x's, it's for the differences. And so notice we just simply call it mu sub d. Mu sub d. So it's the mean. Excuse me. So it's a mean of the population, but it's for the differences. It's not for the x's, it's for the d's. And so we just call it mu sub d. Okay? So that, my friends, is the parameter that we're going to test. So the parameter that we're going to test to make a confidence interval for is mu sub d in section 10.4. Okay, and I know what's going to come up here. I want to erase that. And what we got to think of is that simply mu sub d is equal to mu1 minus mu2. So what you got to think of is that there's a mean for this entire population. Now we only have 15 people here, but if we could get the entire population of all, of everybody who has high cholesterol, okay, and take their average, go ahead and take their cholesterol before and then average it, that would be mu1, right? And then if we could take a look at the average of all the people after they took the pill, that would be mu2. And so notice, remember, all we did was do the subtraction between the two, and so that means the mu sub d is simply equal to mu1 minus mu2. Okay, that's the way we got to think of it. So again, if we can show that mu sub d is greater than 0, we are showing that the new medication is effective in lowering the population's cholesterol. That goes against our brain a little bit, because we see the word lowering and we want to automatically put a less than sign, okay? But I told you common sense prevails with a paired t-test. And what did we find out? Is that a positive D is a good thing here. That is actually showing that the cholesterol is being lowered. Remember, 243, 201. It's lowering here, but it created a positive D. And so if you didn't do this step right here, this statement would be very confusing, because you would go, oh, lowering. Oh, that means we need to show that mu sub D is less than 0. No. Remember, what a positive D means is that's a good thing. That's showing that cholesterol is lowering. Okay, so that's why we cannot skip. Oh, I just accidentally hit my button a couple of times. That's why we cannot skip this problem right here. This step. Okay. Okay, let's move on. So if mu sub D is the population, that's the population mean difference. If that is the parameter, what's the corresponding statistic? Well, when we were testing mu, okay, what was our corresponding statistic that came from the sample? That was x bar, right? But we don't have the x's no more. We have the d's, and so we have mu sub d, and then we have x bar sub d, okay? It's the sample mean for the differences, okay? And that's our statistic. And so that would be, what would that be? That, in this problem, it would be the average of what? These 15 people, for as far as the differences went. Okay, so it's the average of the differences for the sample. I did the calculation down here. I'm sorry that I skipped around there for a second. So here's x bar sub d. That would be the summation of the d's. So if you got your calculator out, you can pause the video. You can add these up, okay, and divide by 15. What would be, why 15? N is being defined as our sample size, as always, but what's our sample size? It's the number of natural pairings that we got going here. We got one person, we got two people, we got three people, we got how many? 15 people. Okay, so if you add that up and divide by 15, I think you get 20.8. What does that mean? Since it turned out to be a positive 20.8, that means on average, okay, for the sample, the cholesterol was lowered by 20.8 units. All right. And what we're going to test here, and what we're going to create a confidence interval for, is that enough evidence to show that for the entire population, the cholesterol would be improved. And that's why we have to test mu sub d and also create a confidence interval for it. All right. So x bar sub d is a statistic. Okay, and we got to calculate that. So here's the steps to conducting a paired t-test. Okay. Hint, these are the same steps when testing mu. It is just that the values of the random variable are not x, they are the d's. Okay, they are the d's. Okay. Step number 1, state the null and the alternative hypothesis. So it's not going to be mu, it's going to be what? Mu sub d. Okay, mu sub d. By the way, mu sub d only applies to section 10.4. Okay, it only applies to section 10.4, not 10.2. So mu sub d is equal to 0. That's what we're always going to state in the null hypothesis for this class. In a higher level stats course, you might not see this being set to 0, But for this course, for these problems right here, that's what the null hypothesis is always going to be. And what does that mean? That means that we're just simply setting mu1 to be equaling mu2. That's it. So mu sub d is equal to 0 is the null. The alternative, we got to figure out, are we going to set mu sub d being less than 0, greater than 0, not equal to 0? So we'll have to figure that in the problem, but that's where those negative d's and positive d's and defining those helps us understand what to put there. Step 2, verify the conditions. So we need some randomness, right? And so we have to pick random people. Basically, you're doing what are you doing? You're picking these random pairings, right? And so you have these pairings, and you're just going to randomly pick pairings. Okay, that's what's going on. So we need to verify the conditions. 1, we need randomness. 2, either we need the d's to be normal. Okay. Now, when we were just testing mu, remember what this was? This was just that either the x's are normal or n was greater than or equal to 30, but x isn't our random variable anymore. What's our random variable? The d's. And so that's why we either need the d's to be normal or we need n to be greater than or equal to 30. Here's the thing, is that we want you to do some calculating here. We want you to calculate the d's, and to evoke the central limit theorem, we would have to have you calculate a whole bunch of d's then. Okay, so I doubt that we're going to do that to you in these problems. And so I doubt that in these problems that we're going to do that the central limit theorem is going to apply too often. Okay, actually probably never, because that's a lot of calculating for you guys to do. So I think what's going to happen here is that we're going to be assuming this a lot, is that the d's are normal in the problem. Step 3, calculate the test stat. So now, remember when we were testing, when we did the test stat, when we were testing mu, we had, hopefully this sounds familiar, x bar minus mu sub 0. Where did mu sub 0 come from? It came from the value in the null hypothesis, right? And so then we have s divided by the square root of n. Okay? Alright, sound familiar? Alright, but x isn't our random variable. What is our random variable? The d's. And so instead of x bar, we have x bar sub d. Instead of mu sub 0, we have mu sub d, but that's still coming from the null hypothesis. And then we have the standard deviation of the d's. And n is n. Okay? Did I change this test statistic around? No. Instead of x's, we have d's. That's it. That's it. That's all we have. Alright? There's our test stat. Okay, and so where's this mu sub d coming from? It's coming from the value in the null hypothesis. And what did we throw in the value in the null hypothesis? 0. So this right here will turn into simply 0. But notice we haven't changed. Oh, by the way, the standard deviation in d's will be given to you in the problem. It's just the standard deviation. Okay, it's the same calculation that we did in chapter 2. It's just that instead of for the x's, it's for the d's. Okay, but it's the same calculation. Okay. Step 4, calculate the probability value. Okay, the p-value. Remember where we got the p-value for when we were just testing mu? Where we got that from? We got it from StatCrunch, right? And we're going to need degrees of freedom because we're working with the t-distribution. And what's the degrees of freedom here? Still n minus 1. Remember what I said. Hint, these are the same steps when testing mu. Okay? It's just that instead of the x's, we have the d's. And so it's the same exact test. It's still going to be the degrees of freedom. It's still going to be n minus 1. Then step 5, compare the p-value to alpha. State your conclusion. Alright, so let's apply this to the problem that we have here. So A, it says test at the 5% significance level if the new medication is effective in lowering cholesterol. Okay, now remember, don't get confused because it says lowering cholesterol, because remember when cholesterol was lowered, what happened to the D's? Remember, that's our focus, is the D's. So yes, the cholesterol was lowered, and what happened to the D? It actually turned into a positive D. So that's what's going to help us to understand then what to put into the alternative hypothesis. Don't get confused that it says lower cholesterol, because you hear lower and you go, oh, I want to put less than. No, for a paired t-test, remember, you have to define the positives and negative D's, okay? And because the positive D means lowering cholesterol, we want to go ahead and test if mu sub D is greater than 0. If you don't understand that, review the last 10 or 15 minutes of the video. listen to it again if you didn't pay close enough attention to that. But that's going to be the alternative. Step 2, verify the conditions. What are the conditions? We need some random pairings, and we did that right here. We have the randomness right here, and either the d's are normal or n is greater than or equal to 30. N is not greater than or equal to 30, and so we would have had to assume this, and so we would have had to state that in the problem. And so in the problem, I would have to state that the differences are normal, and so let's assume this. I had limited space here on the document, on the PowerPoint document here, so I didn't put that, but we would actually had to state that in the problem, that the d's are normal. Okay, so we could verify conditions and continue. Step 3, calculate the test stat, assuming that the standard deviation of the d's is equal to 12.5. Where did that come from? Same formula that we used way back when in chapter 2. Okay, it's just the standard deviation of these numbers. Okay, if you figure out the standard deviation of those numbers, it would have turned out to be 12.5. So let's figure out our test statistic. So we have an x bar sub d of 20.8 minus, like I said, 0. That's coming from the value of the null hypothesis. What's in the value of the null hypothesis for mu sub d? 0. Then we have the standard deviations of d's of 12.5, and we're going to divide that by square root of n, which is square root of 15. I came up with 6.44, but that sounds like a pretty big test statistic. So what does that mean? Our x bar sub d is 6.44 standard errors above the value of the null hypothesis, and that's pretty far away, and that's going to create an awfully small p-value. Okay? So hopefully you're good with that. Now remember, if you're going to do this all in your calculator once, maybe you got to throw some parentheses there. You don't have to do this subtraction. You can just put in 20.8 and then divide by, and then put in parentheses 12.5 divided by the square root of 15, close the parentheses. Okay, let's go ahead and figure out a p-value, and we're going to have to go to StatCrunch, and so reminder here is that our degrees of freedom is going to be 14. Okay, so StatCrunch, you're going to go to Stat, Calculators, and head down to the T. Okay, and so once you put that into your into StatCrunch, okay, now remember you get to choose if either you're going to have greater than or less than, and so since the alternative had a greater than sign, you're going to put in greater than. So you're going to see something like this, is that you're going to see probability, right, and then you're going to fill in this value. You're going to fill in, actually I think it has an X here. I don't know why I just did that, sorry. What it has, StatCrunch has here, is that it has X. I won't draw it. It has an X right here, and then you got to choose either greater than or less than. We're going to choose greater than, then we're going to fill in our test statistic of 6.44. So just like how it's kind of written right here. I should have just pointed to that right there. So right here. So you fill in those things just like this. Okay, we have a right tail test, and we're going to get a very, very small p-value. Okay, and so that's the key, is that we have a very small p-value here. Okay, so step 5, since the p-value is less than alpha, because alpha was set at 5%, certainly our p-value is lower than that, we're going to do what? We're going to reject the null hypothesis. So what did the null hypothesis say? Is that they were potentially equal to one another. Okay, what did the alternative say? So if we reject the null, we think the alternative is correct. What did the alternative say? Is that mu sub d was greater than 0. Fantastic, but what does that mean in terms of the problem? That means on average the pill is effective. So we would say we have strong evidence that the new medication on average will be effective for all people in doing what? Lowering cholesterol. Okay, so there's our hypothesis test. If you got any questions, let me know. But we're going to move on to confidence intervals. Excuse me about that. So we're going to create a confidence interval for the population mean difference. So we're going to create a confidence interval for mu sub d. So confidence interval is the following, and this should look familiar. Instead of x bar, we have x bar sub d, right? Instead of standard deviation, just, instead of s, we have s sub d. Critical value is the same thing. Where we get this from? We get the critical value from the t-table, right? We get the critical value from the t-table. And so let's take a look on our t-table. So here is the t-table. We have 14 degrees of freedom. I think we're creating a 95% confidence interval. Looks like 2.145. And so when you do the critical value, you have to go to the t-table for this one. Okay, 14 degrees of freedom, 95, 2.145. Okay, I think we have everything. Our x bar sub d was 20.8, 2.145 for the critical value. Standard deviation of the d's, what was that? 12.5 or something, and then square root of n, 15, right? Square root of 15. Look familiar? So I think this is pretty straightforward when you put this in your calculator. Okay, you can just say 2.145 times 12.5 divided by the square root of 15. I got a margin, so we got 20.8 plus or minus a margin of error of 6.92. We would add and subtract the margin of error. And so remember, you always do the subtraction first. So I got 13.8 and 27.72 for the confidence interval. And what is that confidence interval for? Mu sub d. So we think mu sub d is located between 13.88 and 27.72. So what does that mean? Let's see. Since it's a positive d, right? So the interpretation is exactly the same as we saw in 10.2. Okay, so if the confidence interval is entirely positive, that means mu1 is greater than mu2. If it's entirely negative, mu1 is less than mu2. And if the confidence interval starts with a negative and goes to a positive, if it includes the value of 0, we have inconclusive results, right? So that means that mu1 could be greater than mu2, mu1 could be less than mu2, mu1 could be equal to mu2, and we don't know which one it is, okay? But we do know what's going on here, okay? We had a confidence interval that was what? Entirely positive, okay? So what is that telling us? Is that mu1, the before, is greater than mu2, the after. And since the before is greater than the after, that's telling us that the pill was effective, okay? And so we would say something like this: we are 95% confident that the new medication on average lowers cholesterol anywhere from 13.88, maybe this to 27.72 for all people with high cholesterol, okay? That probably should be 2, but I'm not going to redo the video at this point. Okay, and so we're pretty sure that cholesterol is going to be getting better for these people. By how much? It's going to get better somewhere between 13.88 to 27.72 units better. So notice that the confidence interval gives us a little bit more information, right? Because it tells us not only is it going to get better, but how much does it, on average, is it going to get better for these people? All right, so there's the first one. Here's the second problem. All right, so if you need to review that one, stop the video, go back, maybe check it through again, okay, and then come to the second one. All right, here's the second one. I have a course in which the students are allowed to retake one of the exams that is administered on a computer in a monitored testing center. To make sure this test does not get compromised, the students' scores are shown but not the individual questions. So in other words, if we don't want them to know exactly what those answers were for those questions, so they can't turn around and give it to their friends or whatever, right? So however, if the students want to see individual questions, they can come to my office and look at their entire exam, but they are not required to. So they can say, hey, Professor Rivolo, I want to do a retake of exam number 2. And I say, are you going to come to my office and check out what you did right and wrong? No. Okay, that's fine. You can go do your retake. And then I do have students that come in, okay, and look at their original exam, okay, and see what they did right and wrong, okay. I'm convinced, okay, but we're going to have to do that empirically, meaning just sort of looking at data, that I'm kind of convinced that the students who don't visit my office don't do significantly better on their retake. Okay, so that's what we're going to be testing. So it says here, however, if the students want to see individual questions, they can come to my office and look at their entire exam, but they are not required to. Therefore, students can take a retake if they come to my office or not. I randomly select 12 students who did not come to my office and decided to retake the test without knowing what mistakes they made. I'm convinced, okay, that on average, students don't do better when they take that that line of attack, if you will. Okay, so here's their first attempt. Here's their second attempt. We have a paired t-test going on here. Okay, same exact people. Okay, first attempt, except second. Okay, and what did they decide? They didn't decide to do anything. They just decided to take the first exam and said, I don't care what I did right or wrong. I think I could do better. All right, well, let's see what happens. So test at an alpha of 5% if the mean test score increased from the first attempt to the second attempt for all the individuals that did not come to my office to view their exam. Okay, so did things get better? Okay, did things increase, or we'll see. Okay, so we have to come up with the differences, right? So I just kind of pushed all that stuff up, the wording of the problem, and I just pushed it into that. And so remember what we have to do. We have to create the difference column, right? So for the first person, 63 minus 65, that's a negative 2. 54 minus 50, that's a positive 4. 61 minus 61, that's a 0. So let's take a look at this. Okay, take a close look at that. Who improved, and what kind of negative? I just said it. What kind of D did they get? And so who improved? This person did, right? They went from a 63 to a 65, and what happened to their D's? It turned out to be negative. And so for a positive D, what happened? They actually did worse. And so in this case, a negative D is actually a good thing. And so remember, I said define what a negative D means. Okay, student did better with the second attempt here. Okay, that's now a good thing. Common sense. What's a positive D mean? Positive D mean that things got a little worse. So that means if mu sub D is less than 0, on average the student did better with the second attempt. And that's why we're going to put that into the alternative hypothesis. So that's why we're going to test if mu sub D is less than 0 in the alternative when we actually run the hypothesis test. Hopefully that makes sense. So if mu sub D is greater than 0, on average the students did better with the first attempt, and that's not good. Okay, and so I think this is why we want to use that for the alternative to see if things got better. Okay. What are we going to have to do? We're going to have to calculate x bar sub D. So we're going to have to average these numbers here, and that would tell the average difference for the samples. So it looks like it turned out to be a negative 1.75. So remember, what a negative means is that things actually got better. Okay, and so that means for our sample, on average, the scores improved by 1.75 points. That's not a great improvement, but we do see some improvement. Is that a big enough improvement in our sample of 15 people to apply that to the entire population? No, we're going to find out. So step number 1, okay, if we already did this step, okay, and thinking this through, we're going to go ahead and test if mu sub D is less than 0. And so what that's telling us is that the first attempt was lower than the second attempt. Things got a little bit better. Okay, so things got better there, things got better here, okay, significantly better there it looks like, because -9, a couple points here, a couple points here. Okay, so that's why we're going to test if mu sub D is less than 0. Step 2, verify conditions. Again, we have random pairings. Okay, I just randomly picked people that decided to do this, and again, we would have to indicate the D's are normal. Okay, because the central limit theorem still doesn't apply. Okay, so we're going to assume that for our problem. Step 3, calculate the test statistic, assuming that the standard deviation of the D's turned out to be 4.267. So I went ahead and calculated the standard deviation of the D's already, gave you that. And so we fill in some values here. We got negative 1.75, minus 0. Again, I would put parentheses around here. Obviously, you do not have to do this calculation up here because it's minus 0. Okay. And remember, n, we had 12 people that I took a look at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we had 12 natural pairings. Okay. So I came up with a negative 1.42. And so what is that telling us is that our x bar was 1.42 standard errors below the value of the null hypothesis. Is that enough convincing evidence to apply this to the entire population? So we got to calculate the p-value. We got to go to StatCrunch to do that. So we would put in 11 degrees of freedom. Do all this stuff again. It's just that this time we're going to put a less than sign. There's our test statistic. And our p-value turned out to be 0.09 essentially, 0.09. Okay. Conclusion. Let's see, p-value is equal to 0.0917. That's greater than a 5%. So we're going to say do not reject the null hypothesis in this situation. And that means we do not have strong evidence that on average grades increase for all students when they decided not to come to my office and look at their first exam. Okay, so what does that mean? Is that, well, mu1 could be greater than mu2, mu1 could be less than mu2, mu1 could be equal to mu2, and so on average, things could get better, or they could actually get worse if they don't look at their exams. Okay, and we don't know which one it is at this point. That's a little disheartening, but that was the case. Okay. Step 2, calculate a 95% confidence interval, okay, for mu sub d. And there's our formula again. And let's see, we're going to have to look up the critical value. We have 11 degrees of freedom. We're going to create a 95. Let's see, 11 degrees of freedom, 95%. I got here 2.201. There's our critical value from our t-table. I throw the numbers into our formula. I got a margin of error 2.71. Okay, we add and subtract that from x bar sub d, and what do we get? We get a negative 4.46 to 0.96. Okay, so what is that telling us? Is that, again, we don't have convincing evidence of anything. mu1 could be greater than mu2, mu1 could be less than mu2. So what that's telling us is that things could get better by 4.46 points, but also it can get worse all the way up to almost a whole point. That's what that's telling us, okay? Or there may be no change whatsoever. And so it could get better, but also, believe it or not, it could actually get worse, okay? So this should be no surprise, okay, that we got a confidence interval that went from a negative to a positive, because that is the equivalent of a hypothesis test of saying what? Not rejecting the null hypothesis, okay, because 0 is a possibility, okay. So that takes us through the second example. All right, if you got any questions, because this might be a little challenging, let me know. All right, and we can always set up a WebEx with you. Thank you for your time.